Waves today. And let's just take a look at a pulse right now to start. So our pulse traveling from left to right, and then from right back to left as it reflects. So let's do that again. I have a positive pulse to the right, comes back as a negative pulse to the left with our fixed end reflection. But what if we continuously do that? So what if we have this oscillator oscillate at just the right rate? Here it's 0.25 hertz. We start to lose the left and right motion. Otherwise, there are waves moving to the left, reflecting, and moving backwards. But I don't see that. I see this one big down and up and back down and up. I see this one big pattern. So this is our first order standing wave that's formed by waves propagating to the right, reflecting back to the left, and interfering with each other. And so let's determine what the velocity of these standing waves are. Well, if you recall, the wave equation is just velocity is frequency times wavelength. So we need to determine the wavelength here. We already have the frequency for this first order standing wave because there's one big antinode here. And here's a node, and here's another node. So let's determine what that wavelength is. So if we click on our rulers, we can see that the distance from start to the fixed end is about 7.5 centimeters. If you recall, the wavelength of a standing wave is node to node distance times 2. So here we have a node, and all the way down to the other node is the full length of that, or 7.5 centimeters. So the wavelength of our first order standing wave, that we have one big section here, first order, one antinode, is going to be 7.5 centimeters times 2, or 15 centimeters. Well, if I take 15 centimeters times 0.25 hertz, I will get my velocity of this first order standing wave, which would be 3.75 meters per second. Let's bump it up and look at second order standing waves. So if 0.25 hertz produces first order, I wonder what frequency will produce second order, or 2 antinodes. Well, if you guessed that you doubled it, you would be correct. So if we bump this up to 0.5 hertz, you see it gets a little funky there. But once we get to 0.5 hertz, we now have two antinodes. Here's one antinode, here's the second antinode, and now you see we have 3 nodes. There's a node in the middle, and the node at the end. So again, these nodes are points where there's not much amplitude, meaning those are areas of destructive interference. These antinodes have huge amplitudes, thus having been formed by constructive interference. See if you can determine the wavelength of the second order standing wave. Well, if you remember, wavelength is node to node times 2. So in this case, I would take from this node to this node, which is just about half of that distance, half of the 7.5 distance, or 3.75 looks like. 3.75 times 2 is going to give you 7.5 centimeters for wavelength. If I do that times 0.5 hertz, I'll get the same wave speed as 15 meters per second. And that's because the speed of a wave is determined by the medium. So these little red and green beads here on the string at this tension, we have that medium tension, produces waves of 15 centimeters per second going down and reflecting back and moving horizontally left to right. Again, you do not see the left to right motion of the waves along the string. You see the result of them interfering in this second order standing wave pattern. We have one antinode and a second antinode here, and our 3 nodes.